now we go into basic quantum mechanics, or as the book titles this chapter, electronic structure and periodic properties of elements. It's really basic quantum mechanics, kind of the introductory to the thought of quantum and where it came from. So we start off talking about light. Light is electromagnetic radiation, or EM radiation. Lots of different types of this type of energy. Light is one of them. Of course, X-rays, gamma rays, ultraviolet, infrared, microwave. Those are all types of electromagnetic radiation. And there's this electronic component and a magnetic component, therefore the name. And it's often illustrated as the electronic wave and the magnetic wave are perpendicular to each other in their direction of propagation. Not important really for what we need to be getting into here. Alright, we start off with the idea though that it is, or has classically been considered, a wave. And so you've got this idea right here of a wave going up and down, and as all waves can be described, it has a wavelength, and that wavelength is the distance from one peak to another peak, like that. Wavelength is often symbolized by the Greek letter lambda, a lowercase lambda. Also, you have the idea of the amplitude. How high up and down is this wave going? Is it just little waves, or are there big waves, right? So that's the amplitude, or lowercase a, amplitude of the wave. And most people will measure that from the middle of the wave, like this, to the top, or to the bottom. Just how much that displacement happening. And then we've got the idea of the frequency over here. The frequency of the wave is related to the wavelength and the velocity at which it's traveling. The frequency is just how many waves occur per second. Okay, so I like to think about if you got this wave, it's going up and down like this, and it's moving past, and maybe you're sitting on the curb watching it go past, the side of the street, and here comes this wave, right? How many wave peaks will pass you in 1 second? So you sit there with your timer and you count how many waves go by in 1 second. That's the frequency. And so the unit would be like, waves per second. We don't usually say waves if we're just counting things. And so just per second, or 1 over s, is the unit then of frequency. That is used so often that it's given its own name. It's called a hertz. H-Z, hertz. Okay, so if someone says, 300 hertz, that means, 300 of those things per second. Every second will happen. Right. Frequency is symbolized by the Greek letter nu. It kind of looks like a V with a small straight side, perhaps. Anyway, the Greek letter nu. So don't confuse that with the letter V, although I don't think we'll be using it at the same time very often. So here in this figure from the textbook, it's showing different examples of these waves. Here we've got a wave traveling. Again, how far do they go in 1 second? All right, so here's this wave in 1 second. This is as far as it goes. And you can see here's lambda from one peak to the next. Now, you could do it from one valley, like here, to the next as well. That would work. Right. And then, how high is it? Well, if you measured right in the middle to the top, that would be the amplitude. And then the frequency. What goes from here and goes down. Here's the next top, and the next top, and the next top. Looks like 3 of them occurred in that 1 second, and so the frequency is 3 hertz. Here's one where, the same amplitude it looks like, but we got double the frequency. It goes twice up and down, where this one only went once for every time, one time that the previous one went up and down. And so this one has 6 hertz as its frequency. Notice that because they're traveling at the same speed, these two, the lambda 2 is much smaller than the lambda 1. So the wavelength from one peak to the next is shorter. Well, that's because they occur more often. The frequency is higher. Now, that's not necessarily true if they were traveling at a different speed, but because they are the same speed here, you have that relationship. Here, frequency is even higher. Here's where they're changing the wavelength now. Here's a shorter wavelength. No, I'm sorry. They have the same wavelength. They're just changing the amplitude. It fooled me there for a second. The amplitude is higher than here. It's a smaller A amplitude. But actually, the frequency and the wavelength are the same for those two cases. All right. Now, the interesting thing about electromagnetic radiation, any types at all, is how fast this wave actually moves. And that speed at which it moves is always constant. It's always the same. That speed has been measured to be 2.998 times 10 to the 8th meters per second. That's really fast. That's an incredibly fast-moving wave. In fact, if that wave went around the Earth, how many times? 1 second, 7.5 times. 7.5 times in 1 second. So light moves crazy fast. But we've measured it, and we know what that speed is. Now, does it always move that same speed in a vacuum? Yes. If you send it through something, like through water, it actually does change the speed a little bit. But that's kind of like the maximum. In a vacuum, that's the fastest it goes, and you never see it go any faster when it's unimpeded, like in a vacuum by matter. So that's kind of interesting, and one of the mysteries of the universe, right? We can never make it go faster or slower unless you put it through something. It's always constant. And so they use little case c to kind of, I think, represent the fact that it is constant. It doesn't change. It's always 2.998 times 10 to the 8th meters per second, and we'll always use that. All right. If you think about the units, wavelength here is meters, frequency is per second. If I multiply those together, I'd get meters per second. Hey, that's exactly what meters per second is. That's the speed. And so you can always have this equation right here where we got c equals lambda times nu. How many meters per second? Right? It's always lambda times nu. Okay, which means also that lambda and nu are inversely related. As one gets bigger, the other one gets smaller. Well, it has to be that way for them to multiply together. I mean, let's say one of them, let's go over here. Let's say one of them was 4, the other one was 10. Right? 4 times 10, that's 40. That would be like the speed, if you will. And so if one went smaller, if I said, hey, let's say my wavelength went from 4 down to 2, my frequency would go up to 20. See, this one's going down, this one's going up, and they still multiply together to get 40. And that's kind of what's happening here. You always get 2.998 times 10 to the 8th meters per second. So as one goes up, the other one has to go down. All right. If you look at all the different wavelengths out there, you get the different types of electromagnetic radiation. So if you look on this scale right here, wavelength in terms of meters, here it is all the way from the gamma rays down here where it's very small wavelengths, 10 to the minus 12. And then you get up to the X-rays. That's somewhere between 10 to the minus 11 and 10 to the minus 8, somewhere in that range. Ultraviolet goes up to somewhere in 10 to the minus 7. And then here's this little rainbow. This little rainbow is the area of light, the wavelengths, that our eyeballs can see. We call it the visible light. All right, so we can see all the different colors. Right? And by the way, those colors are different wavelengths. We see the shorter ones as violet and blue, and the longest ones as reddish and orange. Right? And all the different wavelengths from, well, just that little teeny section right there of the electromagnetic spectrum are what we can see with our eyeballs. All right. As we go larger wavelengths, we get up to the infrared, and then the terahertz, and then the microwave. Cell phone broadcasts kind of in this region, broadcast, wireless radio, very, very, very long wavelengths out there. All right, and so they give all these different kind of, I guess, examples of what fits in these different regions. It's all electromagnetic radiation, though. And we'll talk a little bit more about why is it our eyes can only see in that, or at least why does it make sense that they only see in that. Now here's an interesting thing, energy. The energy, I'm talking about that because it's up here, the energy of in electromagnetic radiation scales with its frequency. And remember, frequency and wavelength are inversely proportional. So if I'm talking about these have very small wavelengths down here, that means they have very high frequencies. And energy goes with frequency. So these guys down here would be very, very high energy. Gamma rays, X-rays, ultraviolet, they pack a punch, right? They have a lot of energy that they carry. Where you get down to these broadcasts and wireless radios, microwaves down here, they have very large wavelengths, which means they have very small frequencies and therefore also very small energy. Right? So these things, not much energy at all. That's why, you know, we can broadcast wireless radio, Wi-Fi, all that kind of stuff all we want. It's not going to hurt us one bit. Very, very low energy. Right? We're up here. Imagine if we broadcast our Wi-Fi up in gamma or X-rays, carrying all that energy, it'd be like constantly flooded with X-rays. Yeah, that could hurt us. Right? So the amount of energy that these electromagnetic radiations carry is important. So always remember that. And here's these arrows that are trying to kind of summarize it. As we increase the wavelength, the frequency is decreasing. The frequency would increase as we decrease the wavelength, actually. And energy goes along with the same direction as frequency. Example 6.1, determining the frequency and wavelength of radiation. So it says a sodium streetlight. So light bulbs made with sodium filament, that's what's producing the light, gives off yellow light and has a wavelength of 589 nanometers. What is the frequency? Alright, well, we know that frequency and wavelength are related by the very simple equation C equals lambda nu. And so we can just fill it in. C is always the same number, 2.998 times 10 to the 8th meters per second, equals the wavelength, 589 nanometers. That nano means 10 to the minus 9. So that many meters times the frequency. And we can solve that fairly easy now. Frequency, go over to the calculator. Frequency would equal 2.998 times 10 to the 10 to the positive 8 divided by 589 times 10 to the minus 9 equals 508.998. So we'll call that 509. And what are the units? Oh, it's times 10 to the 12th. Don't forget that, times 10 to the 12th. And what are the units? This would be a per second. This is a meters per second. I'm sorry. This is a meters. Meters cancel. The unit is a per second. So that light is vibrating at 509 times 10 to the 12th times every second, which is a lot.